Hi, welcome to SVM Kernel function. The mathematics behind the kernel function here given as a dual problem. So dual problem of given objective function. Here we will use the objective function for the m number of samples minus given constraints. So here the alpha I and alpha k are the parameters. Then we will use dot product of the features and dot product of the actual output of the given samples and predicted output. So now here we are taking, assume the first sample is A and second sample is B. Here we are having the feature x1 and x2. Then assume we are going to apply the nonlinear function f of feature x1 and x2. This is the nonlinear function we are going to apply. This is also we should give what is the function we are going to use as a nonlinear function. Here x1 square root x1 x2 and x2 square. Then based upon that, for the sample A we will get a1 square, right? The a1 in the sense the feature, this is the a1, this is a2, so this one is b1 b2 features, right? A1 square based upon this and square root a1 a2 based upon this term and a2 square this term. Like that, for the second sample we will get b1 square root b1 b2 and b2 square. Then here the kernel function is having the property of dot product of transformed data values can be written in the form of actual data dot product values. So that's what we have given here, dot product of given features, right? So we are going to apply the dot product of these features transforming values will be written as a actual data dot product values. This is the actual data. So when you are applying the dot product, you will get finally in this format. So a dot b whole square. So dot product of transformed values can be written in the form of actual data dot product values. So here kernel function takes input as a vector. So this is the vector b1 b2. Okay, b1 b2 is one vector, then a1 a2 is another vector. So which is considering the input as vectors in the original space, and result also will be as dot product of vectors. So this result dot product of vectors, okay, will be given in the transformed space. So that's what get written here. Kernel of a comma b, kernel function of a comma b. A is one sample and b is another sample, so which can be written in the form of a dot b whole square, right? So finally polynomial kernel k of x1 comma x2 can be written as x1 dot x2 plus constant c, then this is degree of the polynomial. So here mostly we will use a radial basis function k of x1 comma x2 exponentiation of minus norm 2. So norm 2 x1 minus x2 divided by 2 sigma square. So mostly we will use radial basis function as the kernel function to get the better classification. Thanks for watching.